Good morning, everybody, and afternoon. Today I want to talk about Chapter 3, and the main concepts are elements, atoms, and ions. And first I want us to look at just a list of some of the elements from the periodic table and their symbols. And you'll see here aluminum has the symbol Al, which is kind of what you'd expect. It's the first two letters of the element name. But then you have antimony, which is SB for its symbol. Argon, AR. Arsenic is not AR because that would be confusing, right? Because argon's AR, so that one is AS. Barium, BA. Bismuth, BI. Okay, so on and so forth. So just getting a little bit more familiar with the element names and their symbols. And also we talked about molecules and how they're expressed in a formula. And if you'll notice these three compounds, we have NO, NO2, and N2O. And remember that if there's no number, then it's understood that it's one. So in the first molecule, we have one nitrogen and one oxygen. The second one, we have one nitrogen and two oxygens. And in the third molecule, we have two nitrogens and one oxygen. Those little numbers below, those are called subscripts. And remember, if there's no number, it's understood that it's just one. I want to talk about the atom and how different scientists helped us to develop our current model of an atom. And the first scientist I want to talk about is Millikan. And Millikan capitalized on one of the scientists in your book. His name is J.J. Thomson. And he used a machine through which he would spray oil droplets. Then he would ionize the air through which those droplets were flowing so that those droplets, some of them, would get a charge from the electrons that had been released from the air. Then those oil droplets were allowed to pass through a hole, and the next space consisted of two charged plates. Now, if those oil droplets had electrons on them with a negative charge, of course they were going to be attracted to the positive side. So in that way, he was able to discover that electrons had a negative charge. Scientists did not know that until he discovered it. He also used a fairly complicated equation to figure out the mass of the electron. Then came William Thomson, also known as Lord Kelvin. So he's a different Thomson last name scientist. He came up with the plum pudding model, which we now know, of course, is wrong. But it was his idea that the electrons were floating in a sea of positive charges. So that was called the plum pudding model because it looked like a plum pudding. The next scientist I want to talk about is Rutherford. And Rutherford used the apparatus you see here to bombard gold foil with alpha particles. And alpha particles have a positive charge. So most of the particles actually went straight through the gold foil. But every once in a while, some of them would get deflected. And he looked at the angles by which they got deflected to figure out that they were getting deflected by something in the middle of the atom. And so since the alpha particles are positively charged and they were getting deflected, they must have been being repelled by a positive charge in the middle. And those positive charges, he determined, were protons. So we can thank him for discovering that atoms have a nucleus in the center and they have protons in the center. He later discovered with Chadwick that there's also neutrons in the center. But the apparatus you see here was how we discovered that the atom has a nucleus in the middle. So if we compare the two models, on the left we have Lord Kelvin's plum pudding model, and on the right we have Rutherford's model. So if Lord Kelvin had been correct, then on the left we see that all of the alpha particles should have gone through with some very slight deflections, whereas on the right we have Rutherford's model, where when the alpha particles encountered that central nucleus, there should be a large deflection, a large bouncing off of the alpha particle. And that's in fact what he saw in his results, that yes, the alpha particles did get reflected when they encountered the central nucleus. And that's how he knew that was correct. Let's look at this diagram of the atom. So look at the nucleus, 10 to the negative 13th centimeters versus the diameter of the entire atom, 10 to the negative 8th. It's not drawn to scale. No textbook can really show a real atom drawn to scale, because if you divide those numbers, okay, that's 10 to the 5th power. That means that the whole diameter of the atom is 100,000 times greater than the diameter of the nucleus, okay? So the electrons are spinning very far outside from the nucleus. Also, let's look at this table. Let's compare the mass of the electron to the proton and neutron. The proton is 1,836 times more massive than the electron. The neutron is 1,839 times more massive than the electron. So the electron's mass compared to those two other particles is what we call negligible. Okay? It's not to say it doesn't matter, but its mass is negligible. Electrons still matter. We would not have chemistry as we know it without electrons, because they're the ones that do the bonding with other chemicals. Okay? In terms of charges, perhaps you remember from middle school, electrons have a -1 charge, protons +1. Neutrons are neutral, so they have no charge. Here we have two different isotopes of sodium. Isotopes are atoms with the same number of protons but different numbers of neutrons. Okay, on the left side we have one isotope of sodium that has 11 protons and 12 neutrons. Okay, on the right side we have another isotope of sodium, and that one has 11 protons but 13 neutrons. They both have 11 protons, they both have 11 electrons. The only difference is their number of neutrons. Here we have one isotope of sodium. The top number is the mass number, that's the sum of the protons and the neutrons. The bottom number is the atomic number, that's the number of protons. And the element symbol in this case for sodium is Na. Recall that the way we discover how many neutrons there are in the element is that we take 23 minus 11 to get 12 total neutrons. So again, in order to determine how many neutrons, you need to subtract the mass number minus the atomic number. Now let's talk about the periodic table. On the left side, the green column, starting with lithium, those are the alkali metals. Please notice that the hydrogen on top, that is not a metal. Hydrogen is a gas. So although it does form a +1 ion like the rest of those elements, it is not a metal. The next column, the yellow column starting with beryllium, those are called the alkaline earth metals. In the middle we have the transition metals, the purple rectangle that you see. They're metals and they form different types of ions, sometimes +1, sometimes +2. That is why they're called transition. The pink column on the right side, those are halogens, starting with fluorine. And the far right column, the purple column, those are called the noble gases. And they're called noble gases because they do not react with other chemicals. They're what we call inert. Each column, such as the alkali metals, the alkaline earth metals, the halogens, the noble gases, those are called groups or families in chemistry. And the significance of putting them in those columns is that every element in the same column is going to behave chemically similar. So they like to react with similar other chemicals. And that's because they have the same number of electrons in their outer shell. So their reactivities are similar. If they're in the same column, they're chemically similar. Here's another way of organizing the elements in the periodic table. So in gray we have the metals, they're solid. In yellow we have the nonmetals, they're gases with one exception, bromine is a liquid. And then we have the blue elements on the stair step, and they're called metalloids or semimetals. And so they have some metallic and nonmetallic properties. And so those are elements like silicon, germanium, arsenic, antimony, and tellurium. So some of these elements exist solo, like we talked about before. So argon would be an example of that. Argon is a noble gas, so it does not want to react with other atoms. On the other hand, we have diatomic elements, such as this one, nitrogen, that we talked about before. You notice each molecule is made of 2 nitrogen atoms bonded together. And here we have oxygen, also diatomic, so each molecule is made of 2 oxygen atoms bonded together. Here we have a list of all the diatomic elements. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So they're going to exist as H2, N2, O2, F2, Cl2, Br2, and I2. So how are you going to know which ones are diatomic? Well, a good way to remember is that here's the hydrogen up on the left-hand corner. It's diatomic. And then all the other diatomic elements form kind of like a 7 on the periodic table, starting with nitrogen, going down to iodine. Here we have the decomposition of water, whereby water is split into diatomic oxygen molecules and diatomic hydrogen molecules by passing electric current through the water. This is what we studied before, called electrolysis. It's interesting to note that the opposite reaction, where hydrogen reacts with oxygen to create water, is actually the basis for hydrogen-fueled cars. And the nice thing about hydrogen-fueled cars is that the only waste is water. Although hydrogen is very flammable, and it is a concern that it would be stored in the back of your car, evidently industry scientists say that they've perfected the storage problem, and it's really an issue of supply of hydrogen now. It's very expensive and energy intensive to produce hydrogen gas that we need for our hydrogen-fueled cars. Here we have the ion charges in the periodic table. Everything in the alkali metals group, starting with lithium, they have a positive 1 charge because they have lost 1 electron. Everything in the alkaline earth metals group, starting with beryllium, they have a 2+ charge because they have lost 2 electrons. Aluminum, gallium, and indium, they have a 3+ charge because they lost 3 electrons. Going over to the oxygen group, oxygen, sulfur, selenium, and tellurium, they all have a 2- charge because they gained 2 electrons. Remember that electrons have a negative charge. So if they gain 2 electrons, then they have a 2- charge. Everything in the halogen group, the fluorine, chlorine, bromine, iodine, the pink column here, they all have a -1 charge because they gained 1 electron. We can test to see if a given compound is an ionic compound or not. For example, here we're testing pure water. When we run an electric current through the water, it does not light the bulb, it does not generate current because water does not dissolve to make ions. On the other hand, when we dissolve salt in water, it dissolves to make sodium ions and chlorine ions, and those do conduct electricity, and therefore the bulb does light because there is electric current generated that goes through the circuit and lights the bulb.